Yeah, so where we're starting is going to be really in these measures of central tendency. And, we'll talk a little bit of philosophy around why statistics. And then we'll get into our basic measures of centrality, and we'll talk sampling a little bit. And sampling will become more and more important as we go forward. Once we're into the distributions, we're going to use sampling as an approach to solving problems, even not just as this thing that we do to get data. Okay, and we'll touch on continuous versus discrete data here as well. That concept will become more important as we go forward, and what you'll see is that this course definitely focuses on the discrete distributions when we get to them. You should always feel free, if you want to look ahead in lectures, there is another branch on our GitHub repo, and I'll just show you how to get to that. A number of people have been, let me just grab that. A number of people have been wanting to work ahead, and I didn't point this out before, but we archive here in separate branches on our GitHub repo. We archive past classes. So you can look at, let's say, the most recent course, which is March 1st. It started March 1st and ran through April 3rd. And, this looks very familiar, right? This is kind of all the same thing. But for all of these, we have recordings in place. So if, for example, you wanted to, after class today, move ahead and look at our next stats lecture and get a head start on it, this is here on summary stats, measures of spread, right? So today we're talking about measures of central tendency. Next time we meet, we'll talk about measures of spread, like IQR, variance, standard deviation, and related items. So all these video lectures are here, and of course, all the way through the course, we have video lectures. So, if you're trying to target the technical interview sooner than later, like if you are actually aiming for the May 17 cohort, and you have it in your mind, you're going to, crunch and try to get that underway and get into that cohort. The sections here that you would work through would be, I can just point this out. You'd want to start probably in this day 14 and continue with day 17, 18, 19, 20, and 22. And basically, that along with basic probability would give you a solid foundation. If you've got the Python skills, of course, would give you a solid foundation going into the technical interview. So I just want to point that out, and I can reiterate that for anybody. I can reiterate that at the end of class for anybody who wants those specifics. I can list those off again. Okay, so we're going to start with just some reasoning here. Why are probability and statistics so important? And there are a number of reasons, but the primary thing to understand is that data science as a profession and a lot of the the world and sub-worlds of data science grew out of statistics. Also out of computer science, but heavily out of statistics. And if we can think of data science as an abstraction of the sciences, right? Maybe you're a biologist or maybe you're a physicist. It's a natural progression to abstract away from that and be a data scientist. You can take those same scientific approaches and apply them in different fields, or similar scientific approaches. You're going to perform analyses. You're going to experiment. Test hypotheses, and you're going to do deep analyses in an effort to understand a phenomenon or a set of phenomena. And I'm going to be speaking a lot in terms of, hey, there's this phenomena, and when I say that, it's just or this phenomenon. And when I say that, I'm talking about, it could be anything. It could be flipping a coin. It could be cars passing on the street. It could be observations of stars in the sky, or stars in images taken from a satellite. So all of these things relate back to statistics, as they do in the sense of being an abstraction of the sciences. Data science really is that. Machine learning really is that. So here are some things that come from statistics: experimental design and reporting. That definitely does. Linear and logistic regression, which are a couple of our naive algorithms that we think about. There's a chance, if we have enough time at the end, I might, not the end of today, but toward the end of the course, I might code those from scratch, so you can see an example of a model that uses continuous data and a model that uses categorical data. And we might even do a non-parametric model like k-nearest neighbors or something like that. Sampling and resampling, which we have a lot of sampling methods in the realm of data science. Those practices are straight out of statistics, and I can't really say that enough, right? Like statistics really defined these ideas of sampling. And then in terms of reporting results, we have confidence intervals. Like we have ideas, measures of uncertainty, and then we have measures of expectation and deviation and things like that. So why do we talk statistics? It's that in a very fundamental way, we are performing in the evolution of statistics toward the abstraction of all sciences. And that's one way to see it. That's how I see it, or tend to see it. Another thing we might do, and this is sort of just seeding the idea, often in data science, we are trying to analyze a phenomenon in order to make prediction, right? So maybe what we have is we have a bunch of data, right? And we feed that data into a model, like a model that doesn't know how to do anything yet. Let's say it like that. And this model kind of puts out another model, okay? It kind of puts out another model that is trained. And, it knows how to do something. And then we take some new data and we put it into that model, and it makes predictions on that data, right? So when we make these predictions, what we get out of this is something that we want to look like the real thing that happens, right? Like if we're trying to predict if a customer is going to buy our product based on features that we know about them, something we know about them, then we want to get that right so that we can allocate resources to pulling that customer through our system and getting them to buy stuff. That's maybe one example. Or if we're trying to predict the failure of a component based on a number of inputs, like maybe there's a certain load of signal that goes through it, and maybe there's some composition of that component, and we have different compositions, and we have different fail rates that we see in our original data over here. We train with that model, and then we get some new data, and we pass it in, and we get predictions on that, and we want those predictions to do pretty well, right? We want that to do pretty well. And if it doesn't do well, if it doesn't meet some threshold of performance, then this is not a good model, right? If we don't meet a threshold of performance, that's not a good model. Well, how do we define a threshold of performance? Well, we literally just define a threshold of performance, right? We just say, hey, we want this to have 98% accuracy or something like that in its prediction of this outcome, or 87% precision in the prediction of this outcome, or we want it to have an error, let's say a mean squared error of less than some value, right? So when we build these models estimate. These models are estimations of a function, right? They are they represent a function. They don't necessarily represent the function that generates the phenomenon, but they represent a function that reasonably models the phenomenon. So what do I mean by that? We have some phenomenon in nature, right? We have something. And we assume that there is a function, let's just call it f of x, that determines values in this thing, or maybe determines outcomes in the analysis of that thing. Like, let's say we just have a series of values, right? Like A, B, C, D, E, etc., right? So this real function in the universe, we assume, represents the analysis of this phenomenon that leads to the outcomes that we are interested in. So here's a way to think about that. Let's say we have the universe of functions. We have all functions in the universe. There is some subset, and we'll talk about this much more later. There is some subset of functions, and there is going to be a function in here that we choose, right? There's going to be a function in here that we choose because it meets a threshold, right? This is the function that we pull out of the universe of functions, and it is a subset of usable functions for that phenomenon. It's not necessarily the best one. It's not necessarily, and it's definitely not the function, right? It's not necessary. Well, there are times where you actually find the function, and it looks something like this, like y equals mx plus b, or, y equals mx cubed plus, nx squared plus b, or something like that. We do sometimes find those exact mathematical functions for the phenomenon, but even when that happens, there's noise in there. There is some minute detail that we can't really account for. And what we find is that we should never really be able to reduce the error to nothing unless we're sort of in a kind of pure math space or something like that. So this is all, that's sampling, if you think about it. We're pulling some sample of function out of, the universe of functions and out of the subset of potential functions, and we're choosing one that works. It's not the only one that works, but it's one that works, and we can choose other ones, and we can choose them from different sets of algorithms as well. So that's a bit of an aside, but that comes back around quite a bit, actually. So what are we going to cover in terms of basic statistics? Well, there's kind of two classes of things that we're going to cover, if I can make that bigger. We're going to cover mean, median, mode in terms of central tendency. Central tendency is exactly what it sounds like. We're looking toward the center of the data. What is that? What does that look like? And we're going to cover ideas of variance or spread. And primarily, so we only have here listed variance and standard deviation. We're also going to cover IQR, mostly because it comes up, I guess you could say. It comes up quite a bit. It appears in box plots, and box plots and violin plots are pretty common to this day. So we are going to cover those two categories. We're going to take it a little bit slow because this is all going to be programming based. And the primary skill that's in development here is really your Python skills. And these are sort of rudimentary. What we're looking at here is sort of rudimentary in terms of the mathematical skills. So, interesting. So on my slide here, I have a LaTeX error, but I don't think it should matter too much. So I'll pull this up and then I'll kind of talk through it. And maybe I'll just draw some stuff out as we go. So the first thing we're going to talk about is the mean. Mean comes up all the time. Very simple concept, and we'll demonstrate how simple this is. It's the sum of the elements divided by the number of the elements. And we've got a little bit of math here, right? We've got this this math showing, let me make sure I can actually screen grab that. Oh, sorry, my screen capture software is being buggy lately. Apologies for that. I can just rewrite this and talk through it. Let me give you a sense of this mathematical representation, and it's going to be more and more important to understand what these symbols mean. And as you continue your progress through data science, you're going to learn more and more symbolic representation. I like to say that if you can code something, you can decipher the symbols. Does that make sense? And you can implement them. And sometimes if you have a description of an algorithm, you can code out that algorithm, then look at the math and understand the math. I think that is a good direction for a lot of people. It does mean that you need to, be pretty decent at programming to take that sort of path. Otherwise, there are a lot of ways to start learning mathematical symbols, and I can give you some resources in that regard if you feel really overwhelmed by them. So this is just 1 over n. Well, what do I mean by n? Let's just make some data points. Let's say we've got 2, 4, 6, 8, 10, and 12. Okay. And we'll say that this is all in the vector A. Okay. I say vector list. We can just say list. And so what we're going to do to get the average or the mean of this, we're just going to add all those elements up and divide by the number of elements. So n here is going to be 1, 2, 3, 4, 5, 6. N is going to be 6, right? 1 over 6. And so this is 1 over 6 multiplied by the sum of all the values from the first value, which I'm going to say is mathematically indexed at 1. Of course, Python indexes at 0, but in math notation, we index at 1. So I equals 1 to n, and that's just going to be the sum of a sub I. So procedurally, what we would do here is 2 plus 4. Well, that's 6. Plus 6 is 12. Plus 8 is 20. Plus 10 is 30. Sorry. Is that right? Yeah. So 20, 30, 42, right? Correct me if I'm wrong. I may have just summed that incorrectly. So this is going to be, this part right here is going to be 42. And we multiply that by 1 over 6. And that's going to be our mean, right? So what's 42 divided by 6? I feel like I should just know what that is offhand. But 42 divided by 6 is, oh my gosh, it's 7. Wow. I really, really should know that offhand. I think that's the one. You know how when you're a kid and there's like one multiplication that you always get wrong? I think that may have been mine. Either way, that is our mean. 7 is our mean. And so when we're thinking about this, okay, well, that's our mean. How do we represent the mean? Well, there are a couple different symbols that we can use to represent it. The primary ones that we're going to talk about are mu, right? That's mu. That's the Greek letter mu. And that tends to mean mean. And then there's x bar, okay? So there's mu and x bar. Why do we have two different symbols here? Well, there's actually a very good reason for that. And this goes back to sampling. So we have a population here, right? And in statistics in general, we don't know everything, right? So a population is like everything. Let's think about this as all the ages of all the people in the world, right? If we knew that, we could give a definitive answer. We could give a definitive mean for that. We could say, well, the average age of all people is this. You know, it's probably somewhere in the 30s. I don't know. We could look it up. But we could give you a definitive answer to that. And if we gave that definitive answer, we would call it mu, okay? This would be how we represent it. we would say, well, mu is the population parameter, is what we call this. However, we don't have all of the data. We almost never do. It's very, very rare that we do, or when we do, it's due to how we define our data, right? Like the ages of all the kids in a classroom. Well, we could get that definitively. We could call the classroom our population, or the ages of all the kids in the classroom the population, and we could give you a population parameter of that. But we can't say that that is representative of all humans in the world, right? We're dealing with a different space. So usually what we're dealing with actually is a sample, and don't be fooled by the size of this. Often the sample is more like that, right? It's tiny in general compared to the population data. And from this, we might take all those values and get something out of it that we'll call x bar. X bar represents the mean, but it's the statistic of the sample, right? Statistic. So x bar is a statistic. We will tend to be dealing with the realm of statistics, not necessarily the realm of parameters to populations. Now, it may be obvious that we want our statistic to be as close to the actual population parameter as possible, in the same sense that if we're looking for a function that can make good predictions, we want that function to be as close to the actual function that that generates the outcome of some phenomenon out in the universe. In the same sense, we want this measurement x bar to be as close to the parameter as possible. And there are a lot of ways that we can try to do that. We can sample. If we have effective sampling from the population, great. If we sample more effectively, like if we sample more items from the population, like this much of the population, of course we're going to start approaching that parameter, right? We're as our sample grows toward the size of the population, we're going to approach the parameter value. But unless we have all values of the population, we're assuming that we're working with a statistic. Okay, so back to the idea of mean. It's pretty straightforward, right? It's you add everything up, divide by the number of elements. So I think that's pretty straightforward. Now there is a caveat that we can throw on the mean, and this is a little bit antiquated, but I think it does make for a bit of an interesting maybe complexity that we can add into a function that we'll write in a minute. There's an idea of the trimmed mean, okay? And the trimmed mean, well, let's look at something where we could use the trimmed mean. If I have, let's say we have A, and A is 7, 3, 4, 1, 943, and 6. Okay. If we take the mean of those numbers, our mean is going to be higher than we want. It's likely going to be much higher. It might not be representative of the actual population data, okay? And it's not really representative of the values that are in here. And so if we want to get the trimmed mean, what we would do is reorder A. We would sort it, right? And we would say 1, 3, 4, 6, 7, and 943. And looking at this, what we might do is get rid of the highest and lowest values, and then take the mean of these remaining values. So that would be a trimmed mean. We would trim by 1 in that case. Of course, this is not the only way to get rid of what we would call an outlier or a non-representative value that's in our data set. There are other ways we could do that. An obvious way would be to look at this and determine, well, that's an outlier, and just get rid of it. Just throw it away. And in fact, that would be more common. So there are advantages and disadvantages to the trim mean. Advantage, obviously, we can combat outliers in our mean. Disadvantage, there might be a good reason why that 943 is in there. There's a chance, a slim chance, that our sample of six elements here, 6 items, that our sample just happened to choose, 5 items that are very, very small, right? Like maybe this is a measurement of the, so in some unit, the measurement of the mass of some bacteria, and we just happened to choose these, 5 small bacteria and 1 huge one, and we're like, well, maybe that huge one's an outlier, or maybe there is a gradient, a smooth gradient between very small bacteria and very large bacteria, and we should in fact either take a bigger sample or take another sample to see, something more real, and maybe that 943 actually does belong there. So we're going to have a breakout, and I'm going to give you 4 minutes on this. You're going to code the mean function, right? You're going to, if you want, as a bonus, you can include a parameter called trim that removes the greatest and least n values. So, for example, it could be, if we're in your function definition, if you said trim gets 3, you would remove the lowest 3 and the highest 3. I think more likely you're going to trim the highest and lowest value. So trim would get 1. So that's an optional parameter if you want to make your function a little more complex. And I will paste in the data, just this little list of A, into the Slack so that you can use that. And I will set a timer for 4 minutes. And if you haven't seen these timers before, it's just a very simple timer for, and when this gets down to 1, feel free to post your finished code. I'll usually ask, actually, let me stop this for a second. I'll usually ask, do people need 2 more minutes? Somewhere around the 1 minute mark. And if you do, put a, thumbs up or something in the Slack. So that, look forward to that as well. And I'll go ahead and start the timer. Go ahead and code the mean function. Give me a thumbs up in the Slack if you want 2 more minutes, and otherwise, feel free to start posting your code. Okay, so let's go through a solution to this. Now, I'm going to solve this both ways. So I'll solve it first just as the mean function. So we're passing in, actually, we'll put a in there. So here's our mean. We're going to pass in a list, and we can simply return the sum of the list divided by the length of the list. So that's pretty straightforward, right? We could just do that, and if we want to see what that is, so let's print the mean of a, and that'll be looks like that's 238.3, right? So when we're looking at this, it doesn't look to me like 238.3 is very representative of the data in here. In fact, it's larger than the second largest value. It doesn't really look central if we're thinking about this as a sample. So I'm going to go ahead and put in this trim parameter. And I'm going to start off by saying trim is 0. So we're going to assume we're not going to trim anything, is what that means for me. And I'm going to make a copy of the list. So list gets list.copy. Also, if you hear me say gets, I don't know if this is the way Clark reads this. When I say gets, that's the assignment operator. So list, in this case, the way I would read this is list gets list.copy. Okay, just so that if you hear me say that, it's not confusing. And I can say if trim is greater than 0, and by default it won't be. If trim is greater than 0, then this copy of the list underscore, is going to get the sorted version of the list. And I'm going to slice this sorted version of the list starting at trim by and going to negative trim by. And essentially what this is doing is if trim by is 1, then we start at index 1 and we go to index negative 1. So we throw away the top and bottom items. So why don't we run this? So a, and then let's trim by 1. Oh, not trim by, that's called trim. I think naturally I would call it trim by, but So what am I doing wrong here? Oh, I see. So I also need to change this return line to be that list underscore. And when I do that, 47.75, I think that's much more clearly representative of these values. Now, it's even still a little bit off to the right, you could say, right? And if we think about this, 220 is pretty high. And maybe we want to actually trim by 2, right? Maybe we want to trim 2 elements off of this. And 26.16 to me looks much more central, right? When we're considering this. So I'll go ahead and paste this code into the Slack. And in general, I'll do this. When I write a function that you might use later, I'll take my version of it and throw it in the Slack so that you can use it. By all means, if you have a version of the function that you want to use, that you wrote, use that. But just so you have it in case you didn't code it up yourself or didn't get there in the challenge. Okay. Oh, and I just want to note this, just point this out really quick. As I'm coding I have a timer that is uploading this code to GitHub. So in real time, if you ever want to snag stuff from GitHub, you can navigate to the Python file under stats and notice this just synced up. And when I click over here, that yellow turned to white. So we know that it's uploaded. Just pointing that out if at any point you want to snag stuff from GitHub as I'm coding. Okay, so let's apply this now. And I'm going to paste in our data. So we've got this story problem. So while I paste in the data, let me make sure I can do that. Here we go. All right. So an article published in some journal considers 2 different air samples testing for some toxin concentrations for both urban households and farmhouses. And these are the concentrations. Maybe, I don't know if this is in parts per million. I don't actually know what that metric is. Doesn't matter. We get a sense of the scale of those. So determine the sample mean for both of these groups. So the sample mean for urban, the sample mean for farmhouse. All that means is the mean, right? If I say population mean, really I'm talking about it's the whole population, right, of data. If I say sample mean, obviously it's a sample that we've taken. And so you're going to determine the sample mean for each group, and then determine the trimmed mean for each group by trimming the smallest and largest value. So that would be applying my function in that case where we have a trim parameter. Okay, so with that, I'll set a timer for 4 minutes and yeah, go ahead and solve that. All right, so I'm going to go ahead and start coding through this. So there are a couple things we're going to do here. We're going to determine the sample mean, and then we're going to determine the trimmed mean. So here's our data. Okay, we've got urban and farmhouse, and I'm just going to make this a little simple, U and F, and of course change that to the assignment operator, make these lists. Although it would be fine to have them be tuples, wouldn't really matter. So we have this function, this mean function, and we can just look at the mean of urban, and we can look at the mean of farmhouse, right? And then, so that's the first part, right? So that would be part A. Oops. And part B is taking these and trimming them. So this would, I could just put 1 here, right? That's our trim. I usually do this explicitly just because it's nice to communicate to whoever's reading your code that, you know, that's what that is. You're trimming by 1. Now, let's look at the output of this. Oh, there's some error. So urban, it's actually U. Okay. Okay, try that again. And we get 21.545455, you know, just on and on for the mean for the urban, and 8.56 for the mean for farmhouse. Trimmed mean 17 versus 8. Now, I'm going to make this look a little bit nicer. Okay, I'm going to make this into an F string, and the reason I'm doing this is to get you into, hopefully get you into the habit of doing this. So let's give this some annotation, right? So this is going to be the mean for urban, and this is going to be the mean for farmhouse. And these numbers down here are pretty ugly, 21.54545454, and so on. What does that 54 mean, you know, way off to the right? Nothing anymore. These are computers. These numbers, you know, we only have a certain number of significant digits. So I'm actually going to round this mean as well. So let's go ahead and round that to, in this case, I'm going to round that to 1 place. That's my, my sense of this, given the way that the measurements are reported, right? We've got just a couple of significant digits. So let's go ahead and also do the trimmed versions of these, and I think you'll see we get something that's a little nicer to read. And I'm just gonna put an extra space in there so we can see it. Oh, F me, okay. Where is that error? Line 22. Huh. Oh, there. Not sure why I'm not seeing this. Anybody see my error here? Oh, I see it. There it is. Okay. All right. Let's try that again. And I probably have the same error down here. Yeah. So on the other end of that round function, try that again. Okay, cool. Now, I'll make this a little bit bigger. We can look at it. And so these lower 2 values are trimmed. The upper values aren't. Looking at this, one of the ways that you can qualify whether it's helpful to use a trimmed mean or whether or not you might have outliers is to compare a trimmed mean to the original mean. And Notice there is a pretty big difference between our urban trimmed mean and our urban not trimmed mean. And if we look at this data, we've got this really high value of 80. Now, is that an outlier? We don't know. We don't know. We have to qualify that through analysis of the phenomenon. Can we automatically determine it as an outlier? Possibly, and maybe we want to do that. It's hard to say. Okay. So let's continue forward with another common metric. And there's sort of this idea that different data is better analyzed through either the mean or the median as the central tendency. Now, I'm going to kind of refute that a little bit. There are a few questions in here that talk about, is the median a better measure of central tendency or is the mean? They give different information. Ultimately, all the median gives is if you sort the data values, it gives that middle value. That's all it does. Procedurally, this is a little trickier in some ways than determining the mean. The mean was easy, right? We just add everything up and divide by the number of items. Median, you have to do a few more steps in there. Okay, so procedurally, what are you doing here? Well, let's think about this in terms of some data. Let's say we've got A, and A has in it 9, 3, 24, 6, 1, 99. Okay, so the first thing we're going to do is sort it, right? And then we get 1, 3, 6, 9, 24, and 99. The next thing we do is we try to find the middle value, right? Well, in this case, we can just do this until we get to the middle. We've got two middle values. So if we have two middle values like this, what we're going to do is we're just going to add them up and divide by 2. We're going to take the mean of those two middle values. Either way you want to think about it. So that's 15 divided by 2 is 7.5. And I want you to notice 7.5 as our median, which, most of the time if we describe this, I'm just going to say MED, median. Although sometimes you might see this symbol, X squiggly, but we don't use that really very much. So the median is 7.5. Notice 7.5 is not in our data. That becomes important later. 7.5. Let's. I think that's enough information in terms of the procedure that I think we can just go into coding. Sort the list, find the middle value. If the list is even, then you take the mean of the two middle values. If the list is odd, you just select the middle value, whatever that is. So let me give you two lists here. Give you an odd length list and an even length list. And maybe I will also just put the simple algorithm up here. I'll put it over here. And you are going to code a function called median. It has one parameter. That parameter is just a list of numbers. You don't need to expect them to be sorted, of course. I think you should have everything you need. If you have questions, ask them in the Slack. And I'm going to set 6 minutes start. If you'd like 2 more minutes on this, put a thumbs up in the Slack, somewhere right around now. Okay, I'm going to add a couple minutes here. Okay, so let's go ahead and code through this. The first thing, I'll need that data. So I've got that odd list and even list. Throw that in there. And yeah, let's just kind of talk through this. So, this is there is a little bit of complexity here, right, in how you write this. A little more complexity than mean, at least. I'll make that a little bit bigger. So the median, we're going to pass in a list of numbers. We're assuming those are numbers. And we're going to make a choice based on whether or not that list is even or odd. Okay? But the first thing that I'm going to do is I'm going to sort that list. And I'm going to use the sorted function for that. I think that's the easiest way to go. We get a copy of it, and we're going to return values from that copy. So in the odd case, if the list is odd, so I can say if the length of the list, mod 2, right, that's going to, well, I could say if this is equal to 1. Okay, I could, that statement is going to, we divide by 2. If there's a remainder of 1, then we know it's odd. Turns out we can just do this. We can say if the length of the list mod 2, because if it's odd, then 1 is going to evaluate as true. If it's even, 0 is going to evaluate as false. And so we can just do that. The thing I'm going to do here is I'm going to get the middle value. So I'll say mid gets the length of the list divided by 2. When you divide by anything in Python, it gives you a float. So I actually want this to be an integer. And why don't we just return that middle value to start with. And then I'll run this function and we'll go from there. So I'm going to work on this kind of incrementally just to make sure we all kind of have a sense of what's going on here. So let's pass in the odd list because that is kind of the easier case. List and int. Oh, there we go. Let's do that. And I just had my parenthesis in the wrong place. Okay, so 4. It might be helpful if I also print out the odd list just to, make sure that 4 is the middle here. So 0, 1, 2, right? 0, 1, 2, 3, 4. 13, 0, 1, 2, 3, 4, 13. That looks like it's working. So in the odd case, we can actually just return the sorted list sub mid, okay? Now, otherwise, we're going to do something a little bit different. Otherwise, we might say, well, we can still get this middle value. And that's going to be the same operation. In fact, if we want, we can throw that operation outside of everything. But what I want you to notice in the event of the even list, why don't we just return mid here? In the event of the even list, which I will change. There we go. In the event of the even list, this is not actually going to be the middle value anymore, right? 0, 1, 2, 3, 4. If we look at this, this is actually the upper middle value, okay? So we want to be clear about what that is. That's the upper middle value. And I can remove, since I'm doing that statement earlier, I can remove it so that I'm reducing my code a little bit. I think it's a little nicer. So we have this middle value. We can take the mean of list sorted, right? So of the middle value minus 1, okay, which would be, if we're thinking about this in order, it's going to be, well, what I should actually print here is the sorted version of the list. It's kind of meaningless to not do that. Why don't I run that again? So, 0, 1, 2, 3, 4. So that upper middle is 13. The lower middle is going to be 12. And so if I take this and add it to the upper value and divide by 2, then this is going to be our median value. So let's see if that works first. 12.5 is directly between 12 and 13. Cool, that looks like it works. The other thing we can do here, and this may not be immediately obvious, we could instead take the mean of these two values, okay? And that mean will just separate, we'll just change that a little bit. So that's the mean of the two middle values. And then we're creating an unnecessary function dependency on the prior function. Oh, whoops. Int object has no attribute copy. I'm sorry, because this takes a list. That's why. Try that again. And we get 12.5. We get the same answer. Okay. So if I want to see, I'll just copy these and put these here, separate them with a quick print statement, and this first one I'll change to odd list. Okay. And I will copy all of this because you'll need it in a bit. Actually, I think you'll need it in our next lecture, but we'll have it in the same file. Okay, let's take a 5-minute break, and when we get back, we'll continue forward. I'll see y'all back here in 5 minutes. Okay, so let's continue with I might skip this next breakout. Yeah, I'm gonna skip the next breakout. It's basically taking that same data that we had before and looking at the medians of both. One of the things that we can consider is, median versus mean. Median versus mean, and which is a better sense of the centrality of the data. But I think I would rather explore that with this next breakout, which is a little bit different. It's a little bit of a different story. So, and it is explicitly asking if mean or median is the better measure. So let me grab the data for this. And I'll paste that in. And then we'll just talk about this for a second. Okay, so an issue of a recent magazine reported home sale amounts for a sample of homes in Alameda, all of which were sold in the previous month. So we're assuming this is home sales for 1 month. Find the mean value of the homes sold in April from this, find the median value, and just give a quick explanation of which you think is better, here, and why, the mean or the median value, and then we'll talk about that. So I'll set a timer for 4 minutes and go for it. Okay, so let's look at this. I need to comment this stuff out. Okay. So let me grab that data again, and why don't I just grab this all the text in this breakout. I'll throw it over here. Okay. So an issue of this recent magazine. These are all home sale amounts in thousands of dollars. And the first thing we're going to do is find the mean. And why don't I'm just going to call this A, or I'll call it house prices, just to be meaningful with it. Now surround the rest of these with quotes as well, and we'll just answer them in turn. Okay, so find the mean value of the home sold in April. Ooh, that looks like it's the answer. For some reason, that's in the notes. So this is easy. The mean of the house prices, and we can just print that, and maybe I will make this an F string and round this, just like that, and we'll round it to, we'll just round it to one place. Let's just round it, sort of a pure round. And let's say house price mean, and then we'll get the median as well. Maybe I'll just throw an extra space in between the two. \n, that means line break. I could just do an empty print statement too, that would work. And we'll just do the median here as well. And whatever we get out of that, we'll use to explore this question at the end. So assuming 582.5 is actually the answer to that second part too. Let's see. Yep. So 620 and 582. And one thing I think is really helpful for this kind of thing is let's just print the sorted version of the house prices. And we can look at it at all of this in context. And maybe I can just even get rid of that new line character. Just do that. Okay. Okay. So looking at this, one of the questions we might ask ourselves is, which value falls more centrally in the data, right? If we're exploring this question of, which is the better measure. Okay, well, 620 is the mean. This should say median over here. Sorry about that. Let's just say median. 620 is the mean. 620 sits right about there, right? That's where our X bar is. And if we look at the median, that sits about there. And, we might offhand say, okay, well, it does look like median here is more central. And that's a fair statement. Does it mean it's better? And really, it's the question of what do we mean by better? And this is where we might ask the question, well, if we were to sample month after month after month after month for some larger window of time, well, maybe we would average the means from that. And if we saw that the average of the means looked closer to this X bar than it did to this median, to me, that would be a better indicator than, whether or not for this particular month, the median or the X bar is more central in the data. That said, these are just two different descriptors on the same sample. So instead of thinking in terms of better, we might not think in terms of better. We might think in terms of, well, the mean is up here, the median is down here, and we can ask ourselves why. here, obviously, we've got this $1.2 million house that looks like it's, it's like twice the value of the next highest valued house. And, that is obviously pulling our X bar to the right. Is that a normal occurrence, right? Is that something that we would expect to see regularly? If it is, then, like X bar might be pretty good. However, it's really who we're talking to and why we're choosing these metrics in the first place. So maybe don't think about it in terms of better or worse, but on this data, median does look more central. It doesn't necessarily mean that it's better. Let's see what this explanation says. Likely the median would be a more accurate summary statistic due to outlier resistance. I kind of disagree with that, because we don't know. This is just one sample. That said, that is a viable explanation. So I'll just leave that as it is. Okay. So the last measure of central tendency that we'll consider is we're going to take a fairly simplistic view of. It's called the mode. And mode is just the most common item. So, if we're going to continue on this kind of drawing path, if we have some animals, AMs, let's call it ANDs, and we have, a frog and a cat. Maybe we have a snake, and we have another cat. And then we have a lizard, and we have another cat. Well, we can't really ask a question like, what is the median animal? Or what is the mean animal here? What we can ask is, what's the most common animal? And that should be obvious that it's a cat. So, we could have that would be our first mode. That would be the most common. We can also have a second mode. Let's say we have another frog in here or something. Then we have a first mode of cat, a second mode of frog, and it's just a descriptor of common elements. Now, mode is going to come up. How do I say this? I'm going to refer often to a modal value in a distribution. That's something that we'll talk about quite a bit later. But for now, let me give you a list to work with. Let's have a list of, let's just do animals, right? And we'll do, frog, cat, dog, beaver, cat. We'll make cat the mode, just sort of make that happen. We'll also have a couple beavers in there, and we'll have a couple lizards in there. Okay. So you're going to write a function called mode that is going to find the most common value in this list, or any list. So let's do 5 minutes on that. And you're going to code the mode function. Okay, so let's see. Let's look at a way to do this. I'm not going to claim that this is the best way. In fact, this way is only going to get us the first mode, and let's just assume that we're fine with that. So what we're going to expect to see is cat. We're going to look for the most prevalent value in this. So def mode, and that's going to be a list. Or it's going to take as a parameter a list, takes an argument a list. And we're just looking for the most occurring value, which let's start off with the assumption that that is the 0th value. That's going to be the first item in that list. And then we're going to check all the rest of the items. So for each item in the list, starting at the second item and going to the end, we can say if the count of that item is greater than the count of the most occurring, then we can update the most occurring, like so, with that item. And we're just swapping, right? We're just swapping if it is more common. And then we can return that most occurring, and I believe that will work. So what's that called? Animals. Let's look at the mode of animals. Looks like it's a cat. So that looks like it's working. Now, the thing is about this, we have cat in here 3 times. We have beaver in here twice. What if we add beaver in again? So now beaver and cat have equal counts. I just want to show you how this function may not do what you would expect it to do. It doesn't give us both. It doesn't give us both of those items. It only gives us one. And so it stays cat in this case. Now, if I change this a little bit, it could be greater than or equal to, and then it's going to give us beaver, right? So you might think about ways to make a better mode function. Maybe you want to make a function that builds a dictionary with the counts of the items and returns as many of those items as it makes sense to return, right? Or maybe you have a dictionary where the count is the key and the items that match that count are the values, right? And so if you have a bimodal distribution like we have here, you're going to get, you're going to get a tuple with, or a list, probably a list, with both cat and beaver. So, those are things to think about. Those are things you can definitely do. You have the Python resources to be able to do that. Okay, so let's talk about sampling just a little bit more. And we're going to use this to sort of further inform what we've already seen with the mean, specifically the mean, because this is going to come back around. So let's say we have some population, and this is going to look a lot like what I drew before, right? That's our population, P. And we're going to create some sample, S, right? And S, let's say that, there's something meaningful about the values in this. Like maybe there are 2 parameters in here. I'll just call them X and Y for the moment. Now, if we're thinking about constructing a representative sample, and that's a very important word here. If we want a representative sample, we're not going to get all those values from right there, right? We're going to, we're going to figure out a way to sample from all over this thing to construct a good sample. Now, something to keep in mind here is that if we are randomly drawing from this population, there's a chance that even if we sample, 10 times, all those samples end up down here somehow, and we don't get a representative sample. So obviously sampling more is better. Sometimes you have kind of, some kind of bifurcated population. maybe we can think about different examples where you have to take a much more measured sampling approach, right? If you're sampling from cars, let's say, you might need, or from vehicles, highway vehicles, you might need to think about classes of highway vehicles first before you start calculating miles per gallon. And so you have these different classes that you sample from in order to make sure that you're getting SUVs and you're getting mid-sized cars and blah blah blah. And you might build your sample from these classes of types of items in your population. So let's kind of illustrate something that can go a little wrong. And remember that when we're building a statistic like the mean, our hope is that we can approach the population parameter, the actual mean of the population. That's not always the goal, but it's generally the hope. We want to include it when we're approaching this. So I'm going to just create a simple sampling process. So I'm going to say from random, import choice. And maybe I'll just make this a little bit bigger. Oof. Code suggestion. Okay. So what choice is going to do is it's going to literally just choose from something out of a list. So maybe I'll do this just to show you what I mean. Maybe I'm trying to choose between 0 and 1. If I do that, I can see that I get 0, and then I get 1, and then I get 1, and then I get 1, and I get 1, and 0, and so on. So that's how choice works. And we'll use that in a second. I'm going to build a sample range, and I'm going to keep this pretty simple. I'm going to get this from the range of 0 to 99, and I'm going to include 99. I'm casting this to a list, not because I have to, but because I think it makes it easier to view if we want to view it. So I'm going to take a number of samples from that sample range. I'm going to say for whatever in range, and I'm just going to take 5 samples, right? So I'm going to take 5 samples, and I'm going to append them. I'll append the choice from our sample range to this samples list. So let's print a couple things. Let's print the mean of the sample range, right? This is, let's imagine this is a population parameter that we are trying to approach. And then I'm going to print the mean from the samples that we just took. And maybe for fun, let's also just look at the median from that as well. So let's say, let's call this, we'll just call this the population mean. We'll call this the sample mean, and we'll call this the sample median, just to keep things simple. And I'm not going to worry about rounding these offhand. I think they'll be fine. Okay, so let's take a few looks at this. And maybe I'll make this a little bit bigger. Okay, so we did pretty good. For 5 samples, we got 49.2, which is very much approaching the population mean of 49.5. Let's try that again. Okay, now we get 61.2 for the sample mean. We get 52 for the sample mean compared to 49.5. Remember, 49.5 is what we would expect, or what we would like to get. And you can see that we're sort of like, we're drifting to one side or the other of that population mean. And what if we only take 3 samples? call this nsamps, and I'm going to set it to 3, and I'll put that in here, nsamps. And let's see how well we do. Okay, 30. So we're not doing as well, like, right? If we take less samples, kind of makes sense. We're not going to do as well. And we can imagine that we're traveling above and below, right? Like here we're getting a sample mean of 10, and our hope is to get 49.5. Now, what happens when we increase this? Let's increase this to 15. I think even with just 15 samples, well, I think we got a bad batch that time, but even when we increase to 15 samples, we are going to do much better. We're going to tighten up around that population parameter. And that intuition is important, right? The more samples we take, the better we're going to do. The better we're going to approach some kind of parameter to our phenomenon, to our distribution, or whatever we want to call it. So keep this in mind. Also, this syntax is going to come back around when we sample quite a bit. For whatever in range, the number of samples. We're going to do something. We're going to collect samples. In this case, we're collecting using this choice function. Okay. And just as a reminder, all of this is in that summary_stats.py file that you can navigate to in the source directory under stats. So, and under 0.1 summary stats. So we can see that right here. Premium prep, SRC, stats, 0.1 summary stats. This code is also in the slides, or something close to it. Not quite the same, but close enough that you can review it there. Okay, so we're going to start thinking about continuous versus discrete, okay? And I like to represent this. I like to represent this in terms of an idea that I'm going to call infinite precision. Okay. When we measure things, we do not have infinite precision. There is some point where we have to clip off our ability to really see. If we measure the height of a tree, we don't say, well, that's 27 meters, 0.13946 to infinite, an infinite number of places. Right? We can't do that because we don't have a tool that will do that. We don't have an infinitely precise tool. But let's imagine that we do. Okay. So starting with that premise, there's some infinitely precise tool out there. We can make a distinction between two concepts: continuous and discrete. Discrete. Now, the key words that I want you to think about here: continuous is in reference. Continuous is in reference, in general, to measurement. Okay. This is where that infinitely precise tool comes from. We measure. We're measuring something, and when we measure something, we get some kind of number line, let's say from 0 to 1, where we have all possible values between 0 and 1. I mean, this could be between 0 and 100, but there's an infinite number of values. And if only we had a measuring tool precise enough, we could find there can't actually be. It's a bit paradoxical. We could never find an exact point in here with infinite precision, but we can assume that there is infinite precision in the measurement of something. So, the types of things that might be continuous. Time. We assume time is continuous. We assume it doesn't boil down to discrete moments. Although video has discrete frames, right? So, and by discrete, I just mean separate from each other. So when we think about continuous, we think about measurement. When we think about discrete, we think about counting. And when we talk about counting, factorial permutations and combinations, and more fundamental counting as well, you'll see that we're only dealing with discrete things when we get there. So the way I'm going to represent this is, again, on a number line, this time going from 0 to 10, and with all these values in between. So 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a little cramped, but that's okay. And I'll just put hashes for each of these. Okay. So the way to think about this, a way to think about this, is there's nothing in between 0 and 1. There is absolutely nothing in between there. You're either 0 or 1. You're not something between them. You're either 1 or 2 or 3. And so I like to think about this as these are discretized. There's nothing in between them, right? It's like counting something. If you have 5 boxes in your room, you don't have 4.3 boxes in your room. You have 5 boxes. When you count people, you tend to not count parts of people, Now, this is interesting in some sense because even though you would say something like there's 97 people in this room, you could say on average there's 94.27 people who come to these events. That's okay to do, right? You can have a mean that has a partial human in it. But if you're counting partial humans, then something terrible has gone wrong in that room. And so we don't think about it in those terms. Okay. Other examples for continuous distributions. I mentioned time. We think about distance. Distance is being measurable, right? We think about weight, mass. Anything like that can be measurable. And I think for counting, really it's like, well, how many of something? How many of something in a discrete sense? How many pets do you have? How many cars are on this highway? Okay. So we have another 8 minutes. And what I'm going to do is look into the next slide deck. So give me 1 second. And I think we can start in on some concepts there. Okay, so I'm going to start off with just, let's look at what we'll cover in measures of spread, and we'll cover this on Saturday. So I'm not going to get too far into this. I'm just going to start with it. We're going to cover something called the 5-number summary, and we have all the tools we need to construct this 5-number summary in our prior functions. We're going to talk about the IQR, which is the interquartile range, which is going to be extrapolated from the 5-number summary, at least in the way that we do it. And we're going to use that IQR to determine outliers in a systematic way. Now, this is a classical way. It's not necessarily how you will, in practice, determine outliers, but it is a way to determine outliers, and that's good. That's fine. And, there's a lot of things like that in statistics, right? If we're trying to say within 99.5% certainty, that a hypothesis is not falsifiable, then we actually choose that 99.5%. We could have chosen 95%. And there are conventions and things like that, but notice there's a lot of hand-waviness in there. There's us defining things and us being critical about what we're looking at. We can be very systematic as well, but we always have a kind of human element in the world of statistics where we're being a little arbitrary here and there. And so an outlier is relative to our definition of an outlier. And then we'll look at variance and standard deviation, which are standard deviation is extrapolated from variance. So we'll think about this first in terms of variance, and we'll see that standard deviation is often a more helpful way to think about things because it's more interpretable for us. However, we're going to think about this somewhat in relation to distance. And, I want to sort of seed this idea that we're very often thinking about distance, some form of distance. And we'll touch on that with variance, but we can think about variance as being heavily related to even Euclidean distance, right? Where, if we have 2 points, we can measure this distance in terms of, we can measure the the distance by the crow's flight between, say, point A and point B, call that A and B, as just, x squared, square root of x squared. Sorry, if I call this A and B and this C, C squared, A squared plus B squared equals C squared. So we can think about this as being the square root of A squared plus B squared. And we're going to see how that is sort of directly relevant to our variance. And let's see. I'll just touch on the 5-number summary right now, and we'll pick that up when we start class on Saturday. Okay, so I'm just going to describe this. There are 5 things in here. That's why we call it the 5-number summary. And this is fairly easy to construct. We have the minimum. And if you think about it in Python, we have a min function. We have the maximum, which, if you think about it, we have a max function. We have the median, and we already defined a median function, right? And then we have Q1, which is the first quartile or the 25th percentile, which is the median between the minimum and the median. So again, we've got a function that's going to help us with that. And Q3 is just the median between the median and the maximum. So we have a function for that as well. So when we code that, it's going to be dependent on prior functions. And we're going to kind of encourage this function dependency to some degree, although often in Python, you don't need to write dependent functions. You do want to write atomic functions, but the trend is more to have functions be able to be usable independently of other functions, if you can, except in the role of helper functions or kind of scaffolded functions. Anyway, that's a bit of a side topic. Let's call it there. I'll stay on for questions. I'm going to go ahead and stop the recording right now.